Dynamical and cohomological obstructions for group actions on three manifolds.
Thank you very much for the opportunity. It's a real pleasure to participate and hear about all the interesting mathematics that is happening in the community. Well, the tradition is to talk about your most recent theorem. I found myself happily distracted recently by three manifolds. Now that I'm doing low-dimensional topology, the reason that I got interested in group actions on manifolds is that it turns out that two very different aspects of diffeomorphism groups and homeomorphism groups, the interaction between two very different aspects is going to be useful to understand group actions. And one of them being understanding diffeomorphism groups as an abstract group, the algebraic structure of the group, which is related to dynamics and geometry on the manifold, hence a dynamical in the title. And the other is the homotopy type of diffeomorphism group, understanding of it by taking the classifying space and using all the interesting tools to understand BDiff. So the theme of my talk is to tell you about the interaction between these two aspects and how it's useful to understand group actions on manifolds, in particular three manifolds. So let me start with a classical notion that goes back to Browder. So I'm going to define what is called the bordism of diffeomorphism groups. So it is what you expect it to be. It's given by pairs of manifolds, say of dimension n, closed. I'm interested in oriented case, and a diffeomorphism of M. This is the diffeo of M. And we say that this is null bordant. So if there is so suppose that this is your M with diffeomorphism F. So you're interested to find n that bounds M, and you can extend the diffeomorphism by capital F. So F. And you take a Dyson union, you get a group, and you are interested in calculating this group. One of the early results in understanding delta n goes back to Winkel-Kemper.
One more n.
One more n?
Before the k.
Before the k. Here. Yeah. Thank you. Says that diffeomorphisms of the sphere is null bordant. So you may not be able to extend it, say, to a disk, but there exists a simply connected manifold that you can extend diffeomorphism of a sphere. And interestingly,
do you always assume that everything is simply connected?
No.
This is, I see.
And one of the interesting things that he proved was that in 4k plus 2, in dimension 4k plus 2, this is not finitely generated. But then Craig actually calculated delta n in all dimensions, in higher dimensions. So here is the interesting calculation by Craig. So maybe I should give numbers. So this is the theorem of Craig. For k bigger than 2, one can calculate in odd dimensions 2k minus 1. There is a map from this bordism group to the usual bordism group, 2k minus 1. This is my notation for the usual bordism group, maybe oriented by saying SO, plus what I'm going to denote by 2k hat. This is the one that is the kernel of the signature. What is this map? It sends the pair of M and F to pair of M and a mapping torus of F. And the theorem is this is an isomorphism. So this is in odd dimensions, and in even dimensions, again, Crack. Let me give it in numbers. So this is maybe 2.1, 2.2. For k bigger than 1, this group is isomorphic to something that Craig calls it the width group of isometries. So I'm going to denote it by, I can be more precise, to the minus k of zz plus, again, 2k hat plus 2k plus 1, if I'm not mistaken. Great. So what this map does, it sends a pair to, so this is a width group of isometries of, free Z module with the symmetric or anti-symmetric bilinear form. Yes.
Do you have some orientability assumptions? Sorry.
Everything is orientable.
Okay.
Yeah.
Okay.
That's my assumption. So this is this sends to the middle homology, a torsion, and a map that is induced by diffeomorphisms. This sends to shifting M by CPK, maybe the signature of M. And this is again mapping torus. So this is an isomorphism. Okay, so he calculated in degree 4, in dimension 4 and higher. In low dimensions, it was calculated by different people, and it was more geometric. So again, as a remark, delta 2 and delta 3 were calculated by Bonahon and Melvin. So this is more geometric and a little bit hard, especially in dimension 2. He uses Thurston's classification of homeomorphism of surfaces. So I'm gonna somehow generalize this notion to bordism of group actions. But before doing that, I want to give you one example to motivate the notion of bordism of group action. So I guess motivation. So here you have one diffeomorphism of the boundary and you're interested in extending it to null bordism. You don't care about a group action on the boundary. So you can consider the following example before I try to motivate it. Suppose that you have a handle body. So handle body is a 3-manifold that bounds a surface. So I'm going to denote this by Hg, and the boundary of Hg is a surface of sigma g. So you can consider diffeomorphisms of the handle body and restrict it to the diffeomorphisms of the surface by just restricting to the boundary. Well, one question that geometric group theorists like is, can we find a section? Okay. So, well, exercise if you get bored. It's a interesting exercise. Show that there is no section using geometric ideas.
Homology count as a geometric idea?
Pardon?
Does homology count
No,
as a geometric
no. I'm going to tell you the homological argument, actually. If you allow yourself, well, when you ask about the group the section in the group level, well, these are abstract groups, so it's just group homomorphism between large groups. You can say I'm interested in a continuous group section. If you allow yourself continuous group section, then that means that you can take the classifying space and try to use homology as Johannes wanted. So, so obstructing continuous group sections, continuous sections. I'm going to tell you about a difference between continuous sections and just group theoretic sections later on. But then you can say, okay, I consider the B diff of the handle body and B diff of a surface. If there is a section, there should be a section also on the level of cohomology. We understand the cohomology of this stably by Matz and Weiss. And it actually, a theorem of Guillen, Saracusa, and Tillman, that the map on the level of cohomology has a large kernel. So Michael, maybe you can help me with the spelling. Guillen.
We know that.
Okay. Is that right? Okay. Tillman. So they prove that all the odd MMM classes go to 0. So I'm going to say kappa 2I plus 1 go to 0. So that means that there are obstructions. Okay? But there are obstructions for more, for easier reason. This map turns out to be not even surjective. Okay? So there are mapping classes here that cannot be extended. So we want to get rid of mapping classes. So one natural question that was asked by Etienne Ghys for what manifolds the restriction map from the identity component.
One more S.
Ah, yes. Thank you. I was afraid to write Etienne because I'm not gonna. So diff 0 of the boundary of M. So there's a restriction map. For what manifolds does this map have a section? Okay.
Take component of the identity. The 0 component of the identity.
Yes. Yes. Maybe I should write it down. So this is the identity component. Thank you. So the first interesting things that was observed goes back to Hermann. He proved the following. So there is an unpublished manuscript by Hermann that you can find its translation on Jaco's website, which is the application of the simplicity of diff of a circle. And he proved the following interesting thing. That diff, so I'm thinking about disk and and a circle. So he proved that diff of a circle, I see infinity. I'm not going to worry about the regularity in this talk, but smooth diffeomorphisms does not act on disk. Well, not only there is no section, it does not even act. Okay? This was generalized by Etienne and Kathryn in old dimension. So they proved that they proved that diffeomorphisms of a sphere never acts on any disk of any dimension. Okay?
Never ask me. You have trivial action.
Yeah, I mean, other than trivial action. Yes.
You mean act smooth?
Smoothly, yes. Yeah, good point, actually. You can use Alexander's trick by just extending everything to homeomorphism. But it doesn't act smoothly. Maybe I should say this. Smoothly, thank you, non-trivially. So let me also mention that... Pardon? So remark, so Ghys and Mann generalized it to all dimensions.
D0.
To all dimensions. Okay. All right. So, theorem. If you have a three-manifold whose boundary is a torus, if M is not diffeomorphic to solid torus, this map has no section, i.e. diffeomorphism of a torus does not act on a three-manifold of any three-manifold. Section. I'm going to tell you more about this theorem actually let me say even for homeomorphism. Remark. Does not have section. When M is not diffeomorphic to the torus, and if it's diffeomorphic to the torus, it also does not have a, for diffeomorphism, it doesn't have a section. So I'm going to erase this. This condition is only for homeomorphism. Okay, this is one part of the main theorem that I would like to talk about. The second thing, we can also do it when we have a sphere boundary. So if again M is a three-manifold and the boundary is two-sphere, there is no action of diff of a sphere on any three-manifold. So I'm just going to abbreviate like this. We don't have the same result as here that also works for homeomorphism. I'm going to tell you more why. Any question about these statements?
Each time you mean as groups?
Yes, yes, not just continuous section.
I have a question. So, and if we restrict here to subgroup of diffeomorphism of T's, so there is no section either to homeomorphism. I mean, in the last
Yes, there's no section, right.
Right.
Even diffeomorphism does not act C0.
But you cannot, you cannot extend that force.
Right, yes. Yes. So I guess as a corollary here, one could also consider finitely generated subgroups and prove that they don't extend. So we can generalize the notion of delta 2 that I have up there. You can consider maybe finitely generated group and consider representation or action of this on a manifold. That means that you have a representation into diffeomorphism of the boundary of some manifold. And then you would like to say whether it extends to identity component to the whole thing. Oh, I actually forgot to emphasize why identity component. So the example that I said, there was a problem with the mapping class. There were mapping classes that cannot be extended. Note that any element in the identity component can be extended. So if you have a, so I'm going to draw a picture here. So if you have a diffeomorphism of the boundary that is isotopic to identity, you can use the color to extend it so that it becomes identity, and then you extend it by the identity. So every diffeomorphism that is isotopic to identity can be extended. Somehow the interesting question is, can we extend the group action? Okay. So then you can define similarly.
So what is FGGP? So what do you mean?
What is
By FGGP, so what do you consider some class of
finitely generated groups?
I see.
Yes. Similarly, we can define, delta n and a finitely generated group to be the bordism of group actions. Asking for the calculation of this is a bit ambitious, but we can say that it's non-trivial in dimension 2. So, for example, I guess a corollary. If gamma is a surface group, this guy is highly non-trivial. There are many non-trivial elements that are not null-borded. Okay. Okay, these are the things that I would like to talk about. Any question? Cool. Okay. So let me start with the dynamical consequences. At the beginning, I said that if you're interested to obstruct continuous group action, you can take the classifying space and try to study the classifying space of a group. Somehow, this is a surprise that we only need to worry about continuous sections. So this is a result of Hurtado. It's a theorem. If the section exists, it's continuous. This is actually quite recent, so this is 2015. This is for diffeomorphisms. So for diffeomorphisms, Kathryn also proved it for homeomorphism. So the same thing holds for homeomorphisms.
Let me repeat to see if I understand. So this is, if the section exists in the category of groups, then it exists in the category of topological groups? Or then it is automatically continuous?
Yes.
Oh.
Is that just for 3 manifolds, or what kinds of manifolds? All manifolds?
All manifolds, yes. This is 2016. So, well, this is very convenient. So you need not to worry about crazy group homomorphisms. So now, in order to tell you about the flavor of dynamical obstructions, let me restrict myself to the case of a solid torus. So I guess example. For a moment, suppose that M is the solid torus. Okay, so we have the identity component of the diff of a solid torus to diff of a torus. Well, my T is S1 cross S1. And we would like to find a section. Let me actually make a remark that this is a deep theorem in foliation theory that these groups are simple. Diff 0 of a closed manifold is simple. This is somehow one of the miracles that happened in late 60s, that as an abstract group this is a simple, so if you can find a section, it's either trivial or injective. Okay? So now I said that because we need not to worry about crazy group homomorphisms, we can take the classifying spaces of these things. Sadly, in this case, well, this has the homotopy type of a torus. So this has a homotopy type of CP infinity cross CP infinity. Using Hatcher's theorem or Smale's conjecture in dimension 3, this also has the same homotopy type. Okay? So I'm going to say Hatcher. This is also CP infinity cross CP infinity. So this is a equivalence. So in that case, we cannot hope for finding an obstruction topologically. Okay? But still there is no action, and I'm going to tell you what is the flavor of the argument that one can use. Okay. So consider the following subgroup. So I'm going to subgroup of diff of a circle. So I'm going to define a subgroup gamma as follows. So it's generated by two elements, f and g, and it satisfies the following relations. The commutator to the power 6 is 1. The commutator of the commutators, I mean, the following is also true. This can be seen as a subgroup of diff of a circle. I guess if you're a geometric group theorist, you're not surprised. If you're like me, you're surprised. I can.
Give a hint.
Yes, I'm about to give you a hint. So you can consider, say, rotation in diff of a circle of order 2. Well, first of all, I said that diff of any manifold in particular circle is simple or perfect. So anything can be written as the product of the commutators. And in fact, if you have a rotation of order 2, you can write it as a commutator of just one, of length 1. So rotation of order pi, you can write it as commutator of 2 elements. This is not hard to do. And then you can, this is a hint, so let me just write it very in a small place. So this is a circle. You can consider the cover of it, order 3. You have your f and g here. You can lift them to f and g in the cover. Then, because this is order 2, the commutator of this to the power 6 is going to be 1. And then you can see that the commutator to the power 2 is a deck transformation. So it's going to commute with the lifts. Okay. So consider this subgroup. Now, I'm going to tell you the idea that this group cannot be lifted. So we have a representation on a diff of a torus. Let me actually write it. S1 cross S1. We have a restriction of diff of a solid torus. Extension. So this is going to act on the first S1 and trivially on the second. So I'm going to just write trivially here. And I want to say that there is no such extension. So the idea is, suppose that there is phi. So phi, I guess idea. Well, step 1. Consider the lift of the commutator squared. The first thing that one has to show is that this has a fixed point. Actually, this also has a fixed point. Dynamical arguments, they care about fixed points. So how do you show that? This is a finite order element. You can put a metric and consider that as an isometry. And then if it does not have a fixed point, then you can actually divide by this action and get a group and get a covering. So the idea is that this is going to be a cover if not, this is a cover. But this group acts trivially on the pi 1 of this, and this cannot happen. Okay? contradiction because gamma acts trivially on pi 1. It's exercise in covering theory. Now that it has a fixed point, I said that it's an isometry, so you can look at the fixed point. It's a three-dimensional manifold. You can look at the derivative. It's going to have a fixed direction. So it's going to have a one-dimensional worth of fixed points. And then you can say that it's going to be circle. So there is a circle of fixed points of this action. And then when you look at the derivative of the action, the following interesting thing happens.
Sorry, so what do you mean gamma acts trivially on pi 1? Pi 1 of which space? Of the Gaussian space or?
On a d2 cross s, d2 times s1.
It actually doesn't preserve the base point, so you don't really have a you cannot really action.
Yeah, it's in the cover. It's going to be some kind of big transformation. We'll exercise. So then, if you look at a fixed point and a derivative of the square, so derivative of phi of the square at the fixed point, I said that there is a fixed direction, so somehow putting a frame on a manifold, you can say that this is a matrix that is like this. It's some 2 by 2 and then 1 and 0, 0. This is a order 3 non-trivial matrix in SO2. But now, when you look at the centralizer of this element in matrices, the centralizer of such things is an abelian group. So the centralizer of this is abelian. So what is the consequence of this? Note that in the group, I said that this commutator squared is going to commute with f and g. So you can look at the derivative of f, extension of f at the fixed point, and derivative of g at the fixed point. There are going to be matrices like this, maybe b1, t1, 0, 0, and then maybe b2, t2, 0, 0. But if you take the commutator of these things, you're going to get 0, which is going to contradict this, because the derivative of the commutator squared is non-trivial. Okay. So the d of phi of the commutator is 0, is identity. Contradiction. Is that intelligible?
You prove that only the commutator of them had a fixed point. And now you say that f and g preserve the same base point.
Because f and g, they commute with this, they're going to preserve the fixed points of this. Yep. Thank you. Questions? Okay, so this is a flavor of dynamical argument to show that groups, such groups do not act on manifolds. But then, well, the goal was to show that you don't have action for any three manifold, not just solid torus. So now I'm going to tell you about cohomological obstruction.
Wait, can I just ask, how did you really use that it was a solid torus?
Just I wanted to kill the action on pi 1. That's it. To find the fixed point. So now, suppose that you have M, and M is not diffeomorphic to the solid torus. I want to tell you about the idea of the following theorem. So theorem that, so note, recall that there is a map from B diff of M to B diff of a torus. And the cohomology of B diff of a torus is non-trivial, and we understand it. So the statement is that in degree 2, there is a kernel. Say rationally. So that means that there's an obstruction to find a group action. What did I do with? So I want to tell you how one can prove that there's a cohomological obstruction.
Do you mean B diff discrete or the B diff with topology?
With topology. Any other question? Right. So I guess sketch. So the first step is, you know, we in tree manifold theory we have the prime decomposition. We can write a manifold in a connecting sum of prime parts. And somehow the first step is to try to understand for one prime factor. Okay? So suppose that M is prime, and prime meaning that you cannot write it as a connecting sum of non-trivial three manifolds. So suppose M is prime, and this bounds a torus, and we want to prove that there's an obstruction. Here, well, we should use some three manifold theory. I'm going to tell you about the ideas. So B diff 0 is a simply connected space. So if you think about this map dually in homology, somehow H2 of this is a pi 2 of B diff 0, which is a pi 1 of diff. So you can think about the homotopy groups of diffeomorphisms. So one thing that you want to show is you want to show that pi 1 of diff 0 of M into pi 1 of diff 0 of a torus is not surjective. Why is that? I'm going to again tell you about the steps. So step 1.1. Well, when you think about three manifolds, there is no way out of doing case by case. So there is a case when there is no center of pi 1, and there's a case when there is a center. So if there is a center, if pi 1 of M has a non-trivial center, then you can use interesting theorem of Waldhausen. You You know, Walthausen was a three-manifold theorist before becoming, I guess, the king of algebraic K-theory. So, by Walthausen, we walled. We know that M is a Seifert fibered space. And then by Hatcher, we understand the homotopy type of diff. So
when you say that, does the boundary of M respect the Seifert fiber?
yeah. So Hatcher says that if M is not diffeomorphic to D2 cross S1, did I assume that? No, sorry. So M, yeah, we have it. If M is not D2 cross S1, then the homotopy type of diff 0 of M is a circle, which is given by the circle action on the fiber. I mean, Seifert fibered, I like singular circle bundles. And this has the same homotopy type, so then you can you can use the long exact sequence of homotopy groups in diffeomorphisms to show that this is not going to be surjective. Okay? So I guess I'm going to just write use long exact sequence of homotopy groups. And then step 1.2, if there is no center, then in a long exact sequence of homotopy groups, what do you get? You go to pi 0 of diff of M rail boundary. And to show that this is not surjective, you want to say that there are elements here that has a non-trivial image. That means that you want to show that den twists around the boundary is going to be non-trivial as a mapping class in a three-manifold. And not only non-trivial, it's also non-torsion. So this is a consequence of loop theorem. So by loop theorem, pi 1 of diff, so let me say den twists around the boundary, is a non-torsion element. In a mapping class of diff rail boundary. Okay? So this is the content when you work for prime, and then when your manifold is not prime, it's connected sum of primes, and then you want to cut your three manifolds into prime parts and then do some sort of inductive argument. So for that, this point of view of resolving the classifying space by considering certain submanifolds into M is very useful. 10 minutes. So I'm going to say, suppose step 2. M is not prime. So this is my picture, I guess, for manifold that is not prime. So you should think of these as three manifolds, and this is S2s and so on. And you want to cut along these S2s to get prime factors. So you can, well, the idea is resolve B diff 0 of M by embedding S2s in M, separating spheres. So you can imagine what it's supposed to be. So I'm going to just briefly indicate how we should do this in the remaining minutes. Any questions so far? So you can define a semi-simplicial space. Let X bullet M be a semi-simplicial space given by tuples of embedding of spheres. So these I's are embedding of S2s in M, separating, and they are disjoint. And, well, you have face maps and so on. So one of the things that you have to prove is that this is, the realization is contractible.
Do you allow parallel spheres here?
Well, there are different versions. But yes, we do. Yep. So the realization of this thing is contractible. If you have a contractible semi-simplicial space, you can resolve your B-diff by acting on this, because diff 0 acts on these things, so you get a resolution given by, I guess, taking the homotopy quotient by the action. And then the realization of this has the same homotopy type as B-diff, and we want to use this resolution to solve the problem. Okay? So how do we do that? I guess, as usual, spectral sequences. One thing to observe is if you look at the following commutative diagram, this homotopy quotient over the torus. So there are degree 2 classes in the cohomology here. It's not hard, but there are some case by case, again, consideration that the pullback of one of the cohomology classes here is going to be 0, because this is, so roughly speaking, this is like the disjoint union of B of the stabilizers of your action. And then when you stabilize some P simplex, you can cut along those spheres and get a simpler 3-manifold, but with boundary, with a sphere boundary. And then you can inductively prove that using what we know for prime, that the pullback to the stabilizer, the cohomology of the stabilizer is going to be 0. But we are interested in the geometric realization of this. So we have a cohomology class. Oh, this does not move. We have a cohomology class in H2. So suppose that we have alpha that comes from the cohomology class of B diff 0 of t of the geometric realization of this homotopy quotient. we want to show that it's 0. This is a class that comes from the torus. We know that it's 0 level-wise. Then if you write down the spectral sequence, you need to argue for 2 other levels of the filtration. Why? I should leave one of them in the other side. So I'm going to just summarize. If you look at the spectral sequence for this thing, I guess H Q of X. So in the spectral sequence, you have a class. You know that it's 0 here. This is a degree 2. It turns out that the first row of this spectral sequence is rationally 0. And then there are non-trivial things here. The reason that the first row vanishes is, what is the first row? It has something to do with the first homology of B of the stabilizer. It's like abelianization of the stabilizers of these spheres. It turns out that if you have a simplex, the pi 1 of the stabilizer of a simplex rationally is 0. This is actually 2 torsion group. So because it's 2 torsion, everything on the first row is going to vanish. Well, I want to actually acknowledge a paper that helped me to understand this. You know, if you have thought about homological stability, there is this well-known paper by Alan Hatcher and Natalie Wall about mapping class group, stable mapping class group of 3 manifolds. It's well known because they invented useful tools for proving connectivity of simplicial complexes. The 3 manifold part is not as well known as it should be. This was very useful because, you know, the literature is quite huge, and there's a case-by-case study. And if you want to learn about the mapping class group of something, there are interesting objects, and you don't know whether everything is known about 3 manifolds or mapping class group of that. There's an interesting part in their paper that say we are going to summarize 60 years of work on mapping class group of 3 manifolds. And that was a moment of being grateful for me. Okay.
Somehow, isn't this the first row? Shouldn't this be more like the first homology of B diff of the stabilizers? So more like pi naught of the stabilizers?
Oh yes, pi naught. Sorry. Yes. Thank you. Thank you. Yes, the mapping class group of the stabilizer. Thank you. And then you have to say something about the first row. I do not, I guess, have time. By comparison, of spectral sequences, alpha, so it does not come from the 0 filtration, doesn't come from the first filtration, and you have to say something about the second filtration. So it does not come from the first one. Okay. Do I have anything left? No? Okay, I stop here. Thank you.
Any questions?
Yeah.
In your main theorem, what happens if you didn't want to lift the whole diffeomorphism group or subgroups of the 2 torus? For example, like the 2 torus itself comes to mind.
It does not lift for the case that is not solid torus. For the solid torus, it extends, but it's just rotation. But for not solid torus,
Can be seen by the same method.
yep.
The dynamical argument that you explained is sort of completely understandable but completely miraculous. How does one come up with such an argument?
Well, I asked Katie. It seems, well, if you're a geometric group theorist, it seems that you're used to these things, not that it's... somehow the intuition is that torsion elements cannot be extended. They are very... they can use torsion elements in a very interesting way. And if you have a hyperbolic surface as a boundary, the problem is that diff 0 of the hyperbolic surface, there is no torsion. So we don't know any argument when the boundary is a sigma g for g bigger than 1. Yeah.
There's nothing else, then let's thank Sam again.